I will now give a presentation titled Creating a Unified Microservices Operational Experience on Top of Kubernetes. Thank you. Firstly, self-introduction. I am tkuchiki from Merpay SRE Team. I am working on a cloud spanner, maintaining OSS called Spanner Autoscaler, and I enjoy writing tools in Go and implement log analysis tools called ALP for fun. Here's the agenda for this session. First, I will explain about Merpay's microservice operations, including the operational challenges of microservices, the scale of the services, the foundation of microservices, and the role of Merpay SRE. Next, I will introduce two examples of how the Merpay SRE team, which operates the infrastructure common to microservices, has worked to improve the operational experience by providing a configuration as data-like mechanism for operations as well. And finally, some of the benefits of unifying the operational structure on Kubernetes will be explained. To begin, I will discuss Merpay's microservice operations. First, let me talk about the challenges in operating microservices. In order to create a scalable organization, each team takes ownership from development to operation of microservices. However, if the operation is left to each team and a disparate system is created, there will be issues like tool development cost will increase, common operating rules cannot be applied, and SRE is not able to follow up. Therefore, we have built a platform to operate each microservice, and by operating on this platform, we eliminate the need to create mechanism for each microservice and apply common operating rules. Merpay's services run on a microservices platform with over 60 microservices and over 1,000 Kubernetes pods. Merpay's microservices run on a platform built and operated by Mercari's Microservices platform team. On this platform, developers take ownership to build and operate the services. Therefore, we have mechanism in place to practice infrastructure code with Terraform to manage GCP resources and to put configuration as data into practice by managing resources on Kubernetes with YAML. Terraform and Kubernetes resources do GitOps. So when a pull request is merged into GitHub, it is applied. Deployment to Kubernetes is done using Spinnaker. In the previous slide, the words IAC and CAD were mentioned. IAC, as infrastructure as code, may be familiar to many of you. But CAD, as configuration as data, does not seem to be so widespread yet. So I will mention this briefly here. Configuration as data is the concept of managing infrastructure as data that declares the state it should be in. Taking Kubernetes doing CAD as an example, Kubernetes users manage resources such as deployment by writing them in YAML. But it is the Kubernetes controller that actually creates the resources. This approach is to clearly separate the data and the layer that handles the data. There is also a config connector to manage GCP resources like Kubernetes resources. If Merpay's microservices platform team is responsible for operating the microservices platform. What is the role of the Merpay SRE team? This includes promoting SLA operations, supporting operations on microservices platform, and operating a common microservice infrastructure. The Merpay SRE team has been working to improve the operational experience of microservice developers as part of its operational support efforts. In this context, we are also incorporating and providing a CAD-like structure for operations. In this session, I will present two case studies of our efforts to improve the operational experience. The first is an example of automating operations by providing Cloud Spanner's autoscale functionality utilizing a Kubernetes custom controller. Before I get into the case study, let me touch on Cloud Spanner. Cloud Spanner is GCP's fully managed relational database. Nodes can be increased or decreased without downtime and can be easily scaled. Merpay uses it as a standard database for microservices. When operating Cloud Spanner, there are often cases where you want to increase or decrease the number of nodes. Since Merpay uses Terraform to manage Cloud Spanner, if the number of nodes needs to be changed, the developer creates a pull request and executes a Terraform apply via CI. We will have no problems when resources are in excess and the number of nodes needs to be reduced. But when the load increases due to increased traffic and the number of nodes needs to be increased, the speed required to complete the response becomes an issue. A developer creates a pull request, waits for CI to complete, review it, merge the pull request, and waits for CI to complete executing Terraform apply, which will take at least 10 minutes. Therefore, we felt it was necessary to scale up automatically when CPU usage reached a certain threshold. To achieve autoscaling, we first considered how to implement a combination of GCP products. Periodically running the process of increasing the number of nodes when a specific threshold is reached by operating CPU utilizing metrics can be accomplished by utilizing Cloud Scheduler, Cloud Functions, and Cloud Monitoring. When combining GCP products to achieve autoscaling, there are two possible methods of operation. The first is to run it on each microservice. Merpay creates a GCP project for each microservice and runs Cloud Spanner in that GCP project. Given the ownership of microservices, it seems natural to let our own GCP project perform the autoscaling process. The second method is to run the autoscaling process in one GCP project and manage Cloud Spanner for multiple GCP projects. In this case, each microservice is not operated by its own developer, but by a centralized SRE. Thus, it appears that a combination of GCP products could perform the autoscaling process. However, there were concerns with each of the two methods. First, when operating in each microservice, there are more things for developers to operate. The autoscale function is necessary for operating microservices, but developers should be able to concentrate on product development. Then, if we choose to operate centrally so that developers can focus on developing the product, the burden on SRE increases. It also undermines developer ownership if SRE review is required every time autoscale settings are added or changed. The combination of GCP products did not seem optimal, so we considered other methods. Therefore, we turned to Kubernetes. If the resources can be managed as Kubernetes resources such as deployment or config map, we can include autoscaling in the existing operational flow, such as reviewing and deploying resources within the microservice team. To manage autoscale settings as a Kubernetes resource, Kubernetes custom controller must be implemented. Kubernetes customer controllers perform processing on a user-defined resources or custom resources. A mechanism called a reconciliation loop compares the declared state with the actual state and keeps them in sync with the state it should be in. This diagram is from the book Managing Kubernetes. It shows a sequence of steps, getting the current status of the resource and changing the current state to match the state declared by the user. Let me apply the reconciliation loop process to Cloud Spanner's autoscaling process. It is the very process of autoscaling when you think of it as taking the current number of nodes and continuously changing it to the number of nodes declared by the user. And I realized that this is similar to the horizontal pod autoscaler, which is familiar to anyone running Kubernetes. Confident that we were headed in the right direction, we implemented a Kubernetes custom controller that would monitor and scale Cloud Spanner while functioning like an HPA. We then released it as OSS under the name Spanner Autoscaler in June 2020. In addition, we released a scheduled scaling function in April 2022, which will allow us to temporarily increase the number of nodes on a set schedule.
This picture shows the operation of a microservice utilizing Spanner Autoscaler. The SRE only manages Spanner Autoscaler, so the burden does not increase even if the number of microservices increases. Developers only need to create custom Spanner Autoscaler resources, and ownership is not compromised as the work is completed within the team. Now for the summary of the first case study. After running Cloud Spanner for a while, we found that there was an issue with the operational flow of increasing and decreasing the number of nodes. Since an autoscaling function was necessary to solve this issue, we showed the implementation methods we considered and talked about how we actually chose to go about it. Now, with Spanner Autoscaler in place, developers can take ownership and manage autoscale settings. If you are familiar with Cloud Spanner, you may have wondered why we are not using it when Google's official autoscaler is available. Therefore, we'll briefly mention the official autoscaler, which autoscales Cloud Spanner using a combination of GCP products and was released around September 2020. Spanner Autoscaler only uses CPU task priorities as a scaling metric. The official autoscaler, on the other hand, can scale not only with that, but also with a 24-hour moving average of CPU usage and storage utilization. This is the architecture diagram. I will not go into a detailed explanation of what each component does, but if you want to combine GCP products and autoscale Cloud Spanner, this is a good way to do it. However, Merpay did not adopt the official autoscaler. The reason is that the issues we raised when we considered implementing an autoscaler in combination with GCP products were likely to occur as well, and we decided that the operational experience would be better if we could manage the autoscale settings as a current Kubernetes resource. Let's now move on to the second case study. This is about improving the operation of Cloud Spanner backups using SRE managed container images. Before we get into the main case study, I would first like to mention Cloud Spanner backups. Cloud Spanner has two backup methods, known as backup and export, respectively. Backups have no performance impact as backups are performed using dedicated jobs that do not utilize the instance server resources. However, as the backup data is tied to the instance, it cannot be moved and can only be stored for a maximum of 1 year. Export, on the other hand, is queried as a priority task and may have some performance impact. However, the data can be stored on any storage and can be kept until it is deleted. Merpay has chosen export due to disaster recovery and data retention time requirements. Cloud Spanner does not have the ability to perform these two backups automatically and regularly. Therefore, they need to be operated from the web console or by executing the API. Sending regular API requests can be achieved by using Cloud Scheduler, so automatic backups are possible in combination with Cloud Scheduler. Thus, it is possible to acquire backups using Cloud Scheduler alone, but there were requirements for Slack notifications in the event of export job failure and for measuring the execution time of export jobs, so implementation of a tool was considered. The options for implementing tools included App Engine's cron service, a combination of Cloud Scheduler and Cloud Functions, or a combination of Cloud Scheduler and Cloud Run, etc. As several members had a lot of App Engine experience, the cron service of App Engine was adopted. After running Cloud Spanner's automated backups in App Engine for some time, a problem arose. Developers did not have the authority to operate App Engine, so SRE had to do the setup. Also, when we wanted to update the configuration, we had to make a request to SRE, and as the number of microservices increased, the burden of SRE increased. This is why we started working on improving the backup acquisition operation. From the point of view of making it possible for developers to manage backups alone, building a deployment pipeline via CI could solve the problem. However, as the App Engine is only used to acquire backups, the deployment pipeline is also dedicated to this. Even though there was no other option, the cost of what we wanted to do seemed very high. Also, if the application configuration is managed in Kubernetes YAML and the backup configuration is managed elsewhere, there is a concern that the number of things to manage will increase and the operational effort will increase. That's why we looked at existing mechanisms. Deployments to Kubernetes are done in Spinnaker, and there is a mechanism on the platform to create Spinnaker's deployment pipeline in YAML. Therefore, by using Kubernetes itself, including the execution of export jobs, it is possible to define the deployment pipeline consistently in YAML, from building and deployment pipeline to setting up backups. In addition, since deployment and other aspects of Kubernetes are also managed in YAML, they can be managed in the same way as applications, providing an operational experience similar to that of microservices. With the policy in place, we set about improving. In order to run what was previously running in App Engine with Kubernetes cron job, we needed container images. When we first deployed it in several microservices, we tried the method of creating an image for each microservice. This method was natural given the microservice principle, but it was time-consuming to create a backup-specific Docker file and build the images. It also seemed wasteful to host it in each microservice, even though the content of the image is the same. For this reason, we decided to use an image created by SRE for use by each microservice. The diagram below shows a backup operation using SRE managed container images. The SRE only manages the container images, so the burden does not increase as the number of microservices increase. Developers only need to create YAML, and ownership is not compromised as the work is completed within the team. Here is the summary of the second case study. Merpay's Cloud Spanner backup acquisition operations were not being operated with developer ownership, and there was high load on SRE. Therefore, we introduced a case study where the environment was prepared so that developers could configure the backup settings themselves, reducing the load on the SRE without compromising the developer's ownership. Lastly, I will discuss the benefits of unifying the operation mechanism with Kubernetes through two case studies. First, by unifying the operations in a Kubernetes environment, they can all be expressed in YAML. This makes it easier for developers to work with YAML, as they only need to manage the YAML. Also, even if there are more things to manage, the base configuration is in YAML, so there is less to catch up on for each tool, and this reduces the operational burden. Above all, the configuration is completed within the team, so there is no loss of ownership. The Merpay SRE team focuses on this when designing the operational structure. This is because when operating a large number of microservices, having an environment where each team can operate with ownership is essential for creating a scalable organization. It also has the advantage for SREs that they can reduce the number of tools and focus on other engineering tasks. Here is the summary. We introduced 2 case studies where the CAD mechanism was incorporated into operations to improve the operational experience. Through the introduction of case studies, we showed how unifying the operational mechanism with Kubernetes provides an operation experience that is easy enough to write and deploy YAML without compromising the developer's ownership. We hope this presentation was helpful for your operations. Thank you for your kind attention.